Hey everyone, and welcome. Have you ever stopped to think about what holds literally everything together? You know, the water we drink, the air we breathe, even you? Well, it all boils down to something called chemical bonding. Today, we're going to dive into the simple rules that make atoms stick together. And it all starts with one big question. So, why? Why do they even bother combining in the first place? Why aren't they all just floating around solo, minding their own business? Figuring this out is really the key to understanding, well, pretty much all of chemistry. And the answer, in a single word, is stability. Yep, that's it. Just like a character in a movie has a motivation, every single atom is on this relentless quest to become as stable as it possibly can be. It's the driving force behind, well, everything. And here it is, spelled out for us. The whole goal is to get the stable electronic configuration of the nearest noble gas. Okay, so what does that mean? Think of the noble gases like helium, neon, argon as the super chill, unbothered celebrities of the periodic table. They've got it all figured out. And all the other atoms? They just want to be like them. So how do they get that VIP status? It's all about following one main rule, the octet rule. It's this idea that most atoms are happiest when they have a full outer shell of 8 electrons. 8 is the magic number. Now, for the really tiny guys like hydrogen, they're cool with just 2. That's the duplet rule. But for almost everyone else, it's all about getting to 8. Okay, so if the goal is a full outer shell, how do atoms actually do it? Well, it really depends on their individual personality traits. And the cool thing is we can actually measure these traits, and they tell us exactly how an atom's going to act when it meets another one. First up, we've got ionization potential. The easiest way to think about this is like an atom's grip strength. How tightly is it holding on to its own electrons? If it has a high ionization potential, you're going to need a ton of energy to pry an electron away from it. This atom does not want to give up its stuff. And then you've got the flip side, electron affinity. This is all about how much an atom wants to get a new electron. If an atom has high electron affinity, it gets super excited when it gains an electron and releases a bunch of energy. It's basically a measure of how welcoming it is to newcomers. And finally, maybe the most important trait for bonding, electronegativity. This is basically an atom's pulling power. When two atoms are in a bond sharing electrons, electronegativity tells you which one is pulling those electrons closer. It's like a constant game of tug of war. And what's really amazing is that these traits aren't random at all. They follow these really clear, predictable patterns on the periodic table. As you can see here, as you move from left to right, atoms get stronger and their pull increases. As you go down, they get a bit weaker. It's this beautiful underlying logic that lets us predict how any two atoms are going to interact. So with all these different atomic personalities, atoms have come up with 2 main strategies to get that stable, full outer shell they're all chasing. It really just boils down to a simple choice. Are they going to share, or are they going to steal? And here are the 2 main paths. On one side, we've got electrovalent bonding. You probably know it as ionic bonding. This is a total transfer, a complete electron heist. One atom with a weak grip just gives its electron away to another atom with a really strong pull. And then on the other side, you have covalent bonding. This is the cooperative approach, where 2 atoms decide to share electrons so they can both complete their octets. But here's where it gets interesting. With sharing, well, just like in real life, not all sharing is equal. That tug of war we talked about, the one driven by electronegativity, it's always happening. And how that game plays out determines what kind of covalent bond we get. So, when you have 2 atoms that are evenly matched, they have similar electronegativity, they pull with the same force. The electrons get shared perfectly equally right down the middle. That's a non-polar bond. But if one atom is way more electronegative, it's going to pull those shared electrons closer to its side. That creates a polar bond, where one side is a little bit negative and the other is a little bit positive. So here's the really cool part. We can take all these rules and actually use them to draw the blueprints for molecules. We can make these invisible forces and connections totally visible on paper. Let's try it out. Let's start with the simplest one possible. Hydrogen gas, H2. Okay, so each hydrogen atom has 1 electron. But remember, to be stable, it wants 2, that duplet rule. So what do? They each share their 1 electron with the other. That way, they both get to feel like they have 2. It's a perfect, equal, non-polar covalent bond. Everybody's happy. Now, what about something like water, H2O? Well, oxygen starts with 6 electrons in its outer shell, so it needs 2 more to get to 8. And each hydrogen has 1 and needs 1 more. You see where this is going, right? The oxygen atom just forms a bond with 2 different hydrogen atoms. And boom, oxygen gets its octet, both hydrogens get their duplets, everyone wins. And the pattern just keeps going. Look at ammonia, NH3. Nitrogen has 5 outer electrons, so it needs 3 more to be stable. What's the easiest way to do that? Find 3 hydrogen atoms and form 1 bond with each of them. That gets nitrogen its full octet. Oh, and notice that pair of electrons just hanging out on the nitrogen? That's called a lone pair. It isn't bonding, but it's super important for the molecule's shape. And this is where it gets really creative. Take carbon dioxide, CO2. Carbon needs 4 electrons, and each oxygen needs 2. Just sharing 1 electron pair isn't going to work for anybody. So what happens? The carbon atom forms 2 bonds with each oxygen. It's called a double bond. They're sharing 4 electrons instead of 2. It's this totally elegant solution that makes every atom in the molecule stable. So, let's just quickly recap. It all starts with atoms wanting to be stable, just like a noble gas. Then, their unique personalities, especially electronegativity, determine if they're going to steal or share electrons. And that sharing can either be equal, making a non-polar bond, or unequal, making a polar one. And best of all, we can actually draw all this out to see how these amazing little structures are built. And that brings us to one last big idea to think about. We've only looked at a few tiny molecules today. But these exact same rules, sharing, stealing, and that magic number 8 are what build everything. The incredible double helix of your DNA, the long, complex chains that make up plastics, all of it. So now that you know the basic rules of the game, what other amazing structures do you think are possible? Thanks so much for joining me.